So let's get it started. Our first speaker this morning is Nate Foster. He's an associate professor of computer science at Cornell, and he's a research engineer at Barefoot Networks, now an Intel company. Nate, as probably many of you know, is also chair of the P4 Language Technical Steering Team. The goal of his research is to develop languages and tools that make it easier for programmers to build secure and reliable systems, and he's going to be talking about an interesting project to do that. His current work then focuses on the design and implementation of languages for programming software-defined networks. Nate, I'll turn it over to you. Take it away.
Great, thanks, Larry. I want to give you a view of kind of what's going on in P4. I'll start with a very high-level view, kind of get down to nuts and bolts of what's been happening this past year in the community, and then tell you a little bit about some research that I'm excited about that I'm working on with folks at ONF and Stanford and Princeton. So Denise already covered this, but let me just remind you again, it's a shame that we can't be together, but due to the pandemic, we're here on Zoom. We're trying to make it as interactive as possible. So we have a Slack channel set up on the ONF Slack. Please join that. You can ask questions during keynotes or during the pre-recorded talks. And we also have a poll. We're going to offer a prize to one of the contributed talks at the workshop that is the most novel use of P4. So we leave this up to your discretion, but if there's a use case or a presentation that you get excited about, please vote on it, and you can find the link on the workshop website for that. Okay, so I want to start with some history. I think if you've been looking at P4, you probably know this history, but if not, I'll try to backfill it in. So about 8 years ago, a group at Texas Instruments and Microsoft and Stanford got together and asked kind of what would an SDN switch look like if we just designed it from first principles. And so the idea was to come up with a switch that's programmable, but still is feasible to manufacture and competes with standard fixed function switches. And they came up with this design, originally called RMT, but later called PISA, for protocol independent switch architecture. And it looks a lot like a standard switch pipeline, but it has a programmable parser and a programmable match action pipeline that can be used to implement lots of different kinds of packet processing. And very shortly after that, the folks who came up with PISA realized there was a nice analogy with some trends that were going on elsewhere in computing. So you can look at general purpose computation or graphics or signal processing or machine learning. And increasingly we see custom chips being designed for the tasks in that domain, and domain-specific languages that are being used to program them. So the question was, could PISA be that custom chip for networks? Would it be a sort of general substrate onto which you could map lots of different kinds of tasks? And if so, is there a DSL that should go along with it? And that's really the genesis of P4, thinking about a language that would let us program these kinds of programmable switches. But one thing that started to become clear in the last, say, 12 to 18 months is that P4 is not just about switches anymore. P4 has been incredibly successful on switches. It's let people who have programmable devices develop new protocols or customize their hardware to suit their use case. It's also seen some use in developing novel applications like in-band telemetry, which lets you get unprecedented visibility into the network, or even doing various kinds of function offloads onto programmable routers. But as exciting as all that is, I think we're really just the beginning of this explosion of ideas. Just like half a billion years ago, when all this extra oxygen that was in the atmosphere caused evolution to really accelerate. And if you look at the fossil record, you see all the early differentiations between different classes of animals and plants and so on really started to accelerate. So I think the oxygen that we have from thinking about the network as being programmable is going to cause us to accelerate and differentiate different use cases and applications. So what might this look like? There's a term that a few of us have coined called deep programmability. It's maybe a fancy term, but it really means something very simple. And that is that finally, after more than a decade of work on SDN, we have platforms where every single element can be programmed. So early SDN gave us a programmable control plane, and we can think about how we divide work, how we compose applications, and how we manage a collection of forwarding elements. And P4 originally for switches, but increasingly now for the end-to-end path, gives us the ability to specify, to define the behavior of every packet going through the network. And so we're rapidly moving to an era where there may be some processing that goes on in user space, say with something based on DPDK. We might have some processing going on in the kernel on the end host, on the NIC, and then on many or all of the switches going on the full path through the network. And so this is really exciting, and it gives us the ability to think about different kinds of functions than what we could do before, at least what we could easily do before. And so things like telemetry, which I've already mentioned, which let us observe exactly what's happening to every packet, all the way from the source in some application, all the way on the path across the NIC, across the switches to the other side. What path did it take? How long did it take to get there? What kinds of state did it encounter as it traversed the network? That's something we can now see, and we can use that information to optimize the network, to debug performance faults, and perhaps even to move to autonomous networks. So I think this is one exciting application, but there's many more, and I think the community is going to be the one that comes up with all these different ideas. So let me tell you a little bit about kind of what's happened in P4 this past year. It has been an unusual year with the pandemic. Normally we'd be in some beautiful meeting hall at Stanford, but instead we're here on Zoom. But the activities of the P4 language group have continued, mostly on Zoom. So we've seen continued evolution of the language itself, of runtime APIs like P4 runtime, as well as systems built on top of P4 runtime. And we've seen the development of new P4 architectures, including the portable switch architecture and the portable NIC architecture. We're seeing new open source platforms be put forth. So both new software targets that can execute P4 programs, as well as tools that might utilize those targets to do various forms of compilation or analysis or optimization. One thing that I'm particularly excited about is last year in my opening keynote, I talked about how P4 at the edge was going to be probably where the action was, and we've really seen these new software targets that are enabling deploying P4 at the edge. In user space, P4 DPDK, and in the kernel networking, P4 OBS, and a bunch of FPGA-based platforms and SmartNICs from multiple vendors. You'll hear one talk in this session from Jane. He's CEO of Pensando, which has a SmartNIC-based platform, and there's other SmartNIC vendors as well as sort of newcomers to the P4 ecosystem, developing P4-based tools for, say, FPGAs. We continue to see development of new applications, everything from hardware offloads of very interesting network functions, as well as using programmability to solve thorny problems like congestion control and security. I'll say a little bit more about those at the end. So let me take you through a rundown of kind of the kind of high points of what's happened this year. So the P4 language has a working group which Mihai Budio chairs along with myself, and we have regular meetings once a month. We have a process by which people can bring new proposals for evolving the language. And we just released a new version 1.2.2 of the language spec. It has a bunch of new features that folks building new programs or new systems based on P4 discover were missing. So new ways of writing parsers, using tables, expressions and statements. We've generalized P4's type system to make it more flexible and expressive. And we've revised several aspects of the spec to make the intended meaning clearer. And so, this is I think it's exciting to see this language evolution being driven by use cases. A lot of the changes that are being made are, someone discovers a sort of, weird case in the language and says, hey, let's fix it. And they bring it to the group and we do it. As well, there's some folks in academia who have been studying P4 from a mathematical perspective, developing formal specifications, and they've also uncovered a bunch of sort of flaws or corner cases that were overlooked, and that's exciting too to see that kind of academic approach being brought to bear on the language. P4 runtime, which is the main low-level API for managing P4 devices, also released a new spec a few months ago. And just the highlights here were they now have a official IANA assigned port number, so you can run all your P4 runtime servers on port 9559, and no one should take that from you. They've studied security in the past year, and the spec now has a detailed treatment of security considerations for servers. They've shifted to inclusive terminology throughout and clarified the role of annotations in the P4 info files, which are the main file that's used to generate the P4 runtime implementations. Another big effort that just got released, I believe today, is the portable NIC architecture. So this is something that's been talked about for a few years. Just like PISA is sort of a reference model for a programmable switch, is there something analogous for NICs? And all of the momentum and interest around smart NICs, brings that question to the fore. So there's a group consisting of folks from, Pensando and Intel and Xilinx and NVIDIA. I participate as a member of Cornell. And Google have been, and VMware, have been kind of bashing our heads on an initial design. This is a picture of it you see here. So it's a pipeline that's intended to be executed on a NIC. It's got network ports over here. It's got host ports over here. Basically this pipeline, we sort of scoped the effort to focus on a pipeline that could implement, say, a virtual switch. So there's much more you could do on a NIC, but we didn't want the design exercise to spiral out of control. So we really focused on, could we come up with this pipeline definition and features that would let us do that? So at this point, we've spent about, I guess, 6 or 8 months bashing our heads on this design. We've settled on this pipeline structure and a collection of externs and some additional features for tables like connection tracking. You can go read the draft, which is on the website now, and you can also see Andy Fingerhut's on-demand talk for a deeper dive on this P&A. As far as where the group is going, you'll notice that this green box here is kind of shaded. You can think of this part of the picture as being really the packet processing part of a NIC, but typically there's also some units that will do what you might call message processing. Not just individual packets, but handling richer abstractions like streams. And we'd like to extend P4 to program things that would go here as well, things like transport implementations. So that's really the next big step for the architecture group, is to figure out what's needed to fill in this box and make it programmable as well. Okay, another thing that the applications working group did is to develop a structure and a repository for hosting P4 open source projects. This is now open. The first couple of projects have been contributed, and they really see 2 categories of contributions being there in the future. So one category is what you might call P4 libraries. So if you are developing a new use case and you come up with some P4 code that you think is kind of general and reusable by others, and you want to bundle it up as a library, they'd be happy to host it for you. So for example, reference implementations of standard protocols, or if there's some network function that you think is sort of canonical and reusable, you could put that in a library and they'd be happy to host it for you. They also are hosting whole P4 systems. So these are more for projects that are still being actively developed. The goal is to kind of put them out there so people can understand them and maybe build on them and even contribute back to them. So one example is the Switch ML project, which is a project using P4 switches to accelerate machine learning training using some in-network computation done by folks at Microsoft Research and KAUST and Intel. So if you have a P4 system and you'd like to kind of get it out there and have it be a community resource, if you're willing to put it under an open source license, you can host it on the P4 Lang P4 apps repository. I just want to call out, this effort is really enabled by things like Intel's Open Tofino. So they've opened up their Tofino architecture definition. It's available free online under a flexible license. And so that's what lets people take real systems that are, say, programmed against the Tofino switch and put them online. Okay, one other thing that I've already mentioned a couple of times, there's these new software targets that have emerged, and both of these will have talks, on-demand talks at the workshop here. So P4 OVS is a new framework for running P4 code in the Linux kernel. It integrates well with the standard networking stack as well as SDN controllers. And there's a full tutorial with folks from ONF and Orange and Intel giving a deep dive on that. So this is pretty exciting because having a path to express P4 processing in the kernel, I think will be an enabler for lots of other novel use cases. And this OVS is a very mature and tested platform. So having the two of them come together, I think is very promising. Another software target is P4 DPDK. So this is a new compiler backend for P4C. And here the name of the game is to really enable fast user space processing on CPUs. And again, there's an on-demand talk by Han Wang and Christian Dumitrescu, which you can see, which gives all the details on that. So stepping back, I think this vision of P4 and deep programmability really requires these kinds of software targets, so that P4 is not just about, say, routers and switches, but also in the kernel and even in user space. And one other thing I just wanted to mention, it's something close to my heart. There's a bunch of academics who have started to kind of realize that P4 is going to be an important language and started to build tools that can do mathematical formal reasoning about P4 programs. So one project, which I know I mentioned last year, but it's now being used as part of every commit to the P4 open source compiler, is Gauntlet. This is from NYU, and they've developed some fuzzers and some techniques like translation validation that can be used to check that compiler passes are correct. And then another system is my group, in collaboration with Andrew Rappel's group at Princeton, have been working on mechanical formalizations of P4's type systems and semantics. So this is being used as part of a DARPA program with Andrew's group, and it's also informing some of the work of the language design working group, helping uncover some corner cases, which I mentioned before. So as far as where the community is going, all of the working groups have kind of clear next steps. For language design, which is the group that Mihai and I chair, the sort of two directions I think are enhancing flexibility. So these software targets don't have the same strict resource limitations as some of the hardware targets. So finding ways to make it possible to express more classes of packet processing or message processing in P4 is something that will require language evolution. And then the other big ticket item, which has been on our plate for a while and really is coming to the fore, is how can we support modular programming in the language? The architecture group has a lot of momentum around PSA and PNA. They're also starting to work on a standard library, so a set of externs that can be common across many architectures. The API working group is pushing on integration of things like P4 runtime with industry standard network OSs. You can hear Maithil Raman and Konstantin Beitz's talk on that, I think, tomorrow. The applications working group, as I mentioned, is trying to cultivate kind of reference implementations and nurture some emerging use cases. And then the education working group is developing P4-based training materials for users around the world. So that's kind of the nuts and bolts of what's been going on in the working groups. I now wanted to quickly cover a few community efforts, which I think will be of broad interest. So one is, it's a tradition now for several years to give an award for someone who has really contributed a lot of their time and energy to helping nurture the P4 community. And so this year, the winner of the Distinguished Service Award is Noah Zubelman from Oxford University. I'll have a little applause track for her. So many of you know Noah. She's been involved with programmable networks for a very long time and with P4 for almost since the beginning. And she's really been an evangelist and dedicated promoter of the language. She's also been deeply involved in the P4 to Net FPGA toolchain, which provides a way to run P4 on open FPGA boards. And she also co-chairs the education working group and has led tutorials at a number of workshops all around the world. So thank you, Noah, for all your contributions. And if you see Noah around in the Slack or in the Zoom, please offer your thanks on behalf of all of us. Okay, a couple of other updates. Staff at ONF have been working hard on improving the sort of community infrastructure to support P4. So as of yesterday, we have a brand new website. It's really beautiful. It's done by a professional designer and kind of rethought all the content. So please check out p4.org. It's got all the stuff we had before, specifications, a blog, details about the community. It also has a few new features. So we have a new ecosystem page, which I'll talk about in a minute, as well as some learning resources and some fun videos. So check that out. This ecosystem tab is something I'm pretty excited about. It's really a one-stop shop for understanding kind of what P4 projects, products, targets, services there are. So you can navigate. We've tried to sort of organize things into this nice hourglass here. Everything from sort of solutions and applications all the way down to hardware. And if you go look at the kind of data side of it, you can search for different categories of solutions, and you get links to different projects. And this is intended to be open, so we've populated it with some initial projects we know about, but please submit your projects or products or targets, and we'd love to have it listed. Another thing I'm very excited about is we have a new discussion forum. This is hosted on a platform called Discourse. If you've used web-based Q&A platforms before, it'll be familiar. We just launched it again about a week ago. And I really encourage people who have questions about the language or work of different working groups or applications or anything, please post here. We have many channels. We've got a Slack, we've got email lists, but this discussion forum is really an archival place where if you ask a good question, it can be answered well by an expert and then can be there for others to use again. So increasingly, we'll be pushing folks to ask questions here, and we hope it becomes a community resource for the language. So I want to tell you a little bit about a neat use case that I'm working on with some folks at Stanford, ONF, and Princeton, in particular the students that and Nick, who you see here on this slide. And this is something that is really using deep programmability to do something quite new. So what we've done is, as part of the ONF Ether platform, which is a platform for sort of building a cellular access network under SDN principles, we've taken a core which consists of some P4 switches, an SDN controller based on ONOS, and then this cellular network management platform called Ether, which all runs in the cloud. And we deployed it in the Stanford Flight Lab. They have a bunch of drones, and they do research on how to fly these drones and control them. So the way this works is their lab has a bunch of cameras, and the cameras all communicate back to a little cluster. There's a motion capture app that runs that kind of figures out where the drones are. That then feeds data to a command module, which gives instructions on where they should go. And then the instructions get shipped out over the cellular network to the drones. And so when this is all working, what happens is that the drones can do these intricate formations. They can fly in a particular pattern. They can go execute different strategies. So what we've been using P4 here is to figure out how to make this network robust to different kinds of attacks that you might imagine in the wild. So one attack, the first one I'll show you, is essentially a DDoS attack. So here, the scenario that we sort of prototyped was where there's an attacker who compromises one of the switches in the network and just pummels the motion capture application with packets, and so it becomes unable to do its job. And what you'll see is that without this data, which is really the brains for all these drones, they won't be able to fly in information, and eventually they'll even land. And what we've been using P4 is to actually use a runtime in-network verification of every single packet. So every single packet is being checked hop by hop to make sure that it's following an allowed path, a legal path. And so with this path-based verification, we can detect that the compromised switch is sending packets that shouldn't be there and block them before they affect the server. And there's a second demo, which I'll quickly show you if I have time, which is just a different kind of attack where instead of flooding the network with traffic, the attacker is now sort of eavesdropping on the network and discovering the locations of the drones, which maybe you don't want some outside entity to know. So let me quickly, I'll just show you the first of these demos because I think I'm a little short on time.
On the left are the drones that will fly around in the tight pentagon formation. And on the right, you see the ONOS graphical user interface showing the network topology and background flows flowing at different rates through the network. In the baseline scenario, we have path verification turned off. The attacker is attempting a DOS attack to the motion capture VM connected to leaf 1, and we see this through the orange flow in the ONOS GUI. But the attacker's packets are getting blocked by firewall rules already installed on leaf 2 by the network operator. So next, the attacker will somehow manage to compromise leaf 2 and install a forwarding rule that allows his attack packets to pass through all the firewall rules installed on all the devices. We see that the attack now gets through and the drones break out of formation. We will also see the attack going through on the owner's GUI on the right soon. The behavior of the drones is visibly erratic, and some drones land before the others. Through this attack, we see that even a single compromised network switch can lead to security breaches. In the next scenario, we look at the same attack, but with path verification turned on. We see that the attacker's packets are still able to pass through leaf 2 because it's compromised, but spine 1 is now able to detect packets taking the wrong path, and it drops them instantaneously. So none of the attacker's packets are able to make it through to the motion capture VM, and the drones remain in formation.
Okay, so I think in the interest of time, I'll skip the second demo here, and I'm happy to share that online, maybe on the Discourse site if folks are interested. So just to wrap up, I wanted to invite people to get involved with P4. We're a very open community, and our goals are really to make P4, the de facto standard for packet processing on any platform. There's no fees to join. We're open to anyone, and the working groups are the place to jump in. I want to briefly thank everyone involved with the workshop. We have a fantastic program, world-class speakers for the keynotes, great contributed talks from academia and industry, and there's a big team that made all this happen. So I'll stop there. Thank you so much, and please enjoy the workshop.
Thanks, Nate. Thanks a lot. So I have to, we got a couple minutes. We're all good in terms of the next talk and everything. So on the demo that you showed us, what was the biggest surprise? What just surprised you in putting all that together?
Yeah, so I think what's kind of exciting to me is that there's all these ideas in the software community about how we can, say, protect or secure software. And really what that demo is showing is how we can take the idea of a runtime monitor and apply it to every packet. So you can think of every packet as sort of running a little checker that says, am I allowed to be here at every hop? And the way that gets realized is we use, the end-to-end programmability we have through P4 to deploy the checking logic that does that. And we can deploy that checking logic in a way that's independent of sort of the other parts of the switch that are programmed. And so I guess, for me, there's sort of these two things. Intellectually, it's really cool to have a substrate where you can just take a classic idea like a runtime monitor and now, run it in a network. And okay, there's a little bit of overhead to keep the checking logic, on the programmable switches and get their associated memory and so on. But it's not prohibitive. And it doesn't compromise the performance at all in terms of throughput or latency. There's no real difference. So I think to me, that's kind of what's most exciting. And then looking ahead, what could you do with this? I think, one pushback that sometimes people have for ideas like SDN is, if we make the network more programmable, we're going to make it more complicated. Will we maybe increase the number of faults or, make it hard to run a network reliably? And so I think bringing some of these ideas like runtime monitoring or runtime verification can help to give us some assurance that, doing this is not crazy. So, you can start to imagine accepting, controller code from someone you don't completely trust, or even data plane code from someone you don't trust, because you know that your checking code is running side by side.
Great. So I've got a question from the audience that I think it would be a good one to have you comment on, which is everything you've shown us obviously is quite interesting, but where can someone go to get training in P4 and come up to speed on all of this?
Yeah, so there's a couple of places that I'd recommend. So one is there are a set of tutorials which have been run sometimes at this workshop, sometimes at academic conferences like SIGCOMM or EuroP4. And now there are videos and starter code available online. So if you're brave and want to just try those on your own, you can follow those. There are also, of course, training programs for specific platforms. So the vendors that supply P4 enabled platforms usually have detailed training programs that teach you how to program P4 for their particular device. I believe some of those are posted on the ecosystem tab on the new P4 website.
Does that ecosystem tab point to the Ether Foundation as another way of people getting involved? I don't recall.
I don't recall either, actually. I have to ask Denise or Michelle who set it up, but I think it's been seeded with a bunch of preliminary projects, but if it's not there, anyone is welcome to submit a new element of the ecosystem, and we'd love to grow it out so it become, as I said, the one-stop shop for understanding kind of what P4 targets are out there, what P4 services. So if it's missing, let's get it there.
Yeah, that's going to be a great resource. A narrow specific question is someone asks if using RPF checks for path, if you're using RPF checks for path verification.
Yeah, so we're not actually, we have our own scheme. We're basically taking the controller's view of what function each switch should be implementing, and then compiling that into a compressed checker. So we don't sort of just replicate the forwarding rules and so on. We actually compress it a bit, and then deploy that in a reserved part of the P4 pipeline. So I think you could do what the questioner is answering. That's actually an interesting idea to look at the difference between those two mechanisms, but our mechanism is working a little bit differently.
Great. So I want to have one final question, and then we'll move on to the next speaker, which is, I know you've had some recent work published about the ability to prove things about the programs that you're running, which I think is one of the real potential advantages of P4. Could you just comment on that really quickly?
Yeah. So I think in other domains, we're increasingly seeing the value of having architectures and ISAs and languages that come with formal specifications. So this has been done for example, ARM's ISA has been mechanized. There's a runnable specification of exactly what every instruction does. There's things like C compilers that can prove that the assembly they generate implements the semantics of the source. And people who are building high assurance systems increasingly are taking the critical components and building them out of these, if not end to end, at least sort of big chunks of the system, satisfying some at least functional spec. And I think networks are such critical infrastructure, and P4 is such a wonderful domain specific language with a fairly high level and declarative style to it that we'd sort of be idiots not to do that. So that's really what I think all the people who are working on P4 verification are trying to help happen. And I think that this can have a couple of benefits. I mean, for people who are building critical infrastructure, you'll be able to, reason about properties of a particular P4 program, or prove that a compiler is not somehow, silently injecting some code into your program that wasn't supposed to be there. And it can also, maybe on a slower time frame, help inform design. So we've already seen a little bit of this with the way that the projects like Gauntlet and Petra are helping the P4 language group do their work. Often the task of formalizing a language completely, you have to cover every single case. You have to do it in a way that's kind of elegant enough and streamlined enough that it's tractable to think about the whole language. And that can help give you some guidance when you're struggling with how should we add this new feature. Sometimes the mathematical formalization will give you some point in one direction or another. Great.
That's great stuff. Thanks, Nate. I think it's probably virtual applause, and move on to the next talk.